It's an important theorem in that it allows us to determine non-dimensional parameters. So far in dimensional analysis and similarity, we mostly looked at things like Reynolds number, lift coefficient, Mach number. But now we're going to learn a systematic method to take a problem and distill it into its core non-dimensional variables. Key points from that last lecture where we talked about similarity. Okay, so the overall idea behind this part of the course is to predict design scale performance using experiments. Usually this looks like we test some sort of scale model, we measure its performance, we non-dimensionalize that performance, and then assuming we designed our test right, we can redimensionalize the performance by using the design scale parameters. And the important thing is that requires similarity between design and test scales. In some cases, it's justified to have incomplete similarity. So remember, similarity is geometric similarity plus dynamic similarity. So in some cases, it's okay to not match all of your non-dimensional similarity parameters. And that's because sometimes your performance parameters are independent of those similarity parameters. For example, generally when we consider flows incompressible, we don't need to exactly match the Mach number because we're assuming that those performance parameters are kind of independent of Mach number for a certain Mach number regime, usually less than 0.3. In very special cases, we get Reynolds number independence. So Reynolds number independence means even as we increase, say, the turbulence, the velocity, the mixing in our flow, the non-dimensional performance parameters don't change. So I kind of gave you a drawing last lecture of lift in, I think it was drag coefficient as a function of Reynolds number. So this is a figure from the Frank White fluid mechanics book here. It gives drag coefficient as a function of Reynolds number. So again, a non-dimensional performance parameter as a function of a similarity parameter for a couple of different shapes. So for the sphere, which is the lower line, you can consider this drag coefficient Reynolds number independent kind of when you're along this line. So since, sometimes it's hard to test exactly at the Reynolds number we want to match, say we can only test at a Reynolds number of 10 to the 4. If we know that it's Reynolds number independent, that means our results would be valid for a design scale Reynolds number up to, say, 5 times 10 to the 5 here. Same thing, the cylinder kind of fluctuates a little more, but there's a little bit of independence that maybe could be assumed in this regime, or it depends how accurate of an estimate you're trying to get. If you're trying to get a really precise estimate, you probably want to be really careful about assuming Reynolds number independence. But if you're trying to get that like plus or minus 25% number, Reynolds number independence, you might be able to assume that in some cases. You can also see interesting here. Remember when I talked about inducing the turbulent boundary layer for some shapes can reduce the drag? So here, the Reynolds number, this is the Reynolds number based on diameter. So rho times u times diameter of our cylinder over mu. When the boundary layer on this cylinder or the sphere transitions to a turbulent boundary layer, then we get reduction in drag. And that's because the wake probably decreases in size because the boundary layer remains more attached. So this is kind of for a very smooth case, but this sharp drop-off could be achieved at a lower Reynolds number if you had something to induce turbulence in the boundary layer or energize the boundary layer, for example, vortex generators. Are there any questions about this Reynolds number independence figure? Okay. That was just an extra note on Reynolds number independence because it's quite important. Today we're going to talk solely about Buckingham pi theorem, and this will finish module 3. So ideally this is the last, I'll say from my point of view, this is the last time I'll give you new information that will be on the midterm. I'll review everything on Friday, but I know sometimes in the midterm review lecture, you might see something new to you. Okay, so the learning objectives are just one. So we're going to apply Buckingham pi theorem to generate non-dimensional relationships in this lecture. So an important thing to understand about Buckingham pi theorem before we get into it is that it doesn't tell you what the functional relationship is. If you kind of assume that there's a relationship between different variables, Buckingham pi theorem just kind of distills that down to the non-dimensional variables. It doesn't tell you what the actual functional form of that relationship is. Okay. So before I begin, I just want to make a change to the notation I was using. So if you go, I don't know if you have your notes with you today, but if you go to your notes, um, last lecture's notes, right at the end when I stated Buckingham pi theorem, so I gave, this is still the same theorem, it's just usually, so I said a problem with n variables and k dimensions has n minus k groups. Usually you actually call it, instead of k, j dimensions. So I'll repost these notes, but j dimensions, so has n minus j dimensionless groups. So just a small notation change. This is just if you're Googling things with Buckingham pi theorem, this is normally the notation that's used. So n minus j. Okay, so Buckingham pi theorem. If you're curious, this is a theorem from 1914, so a long time ago. The key idea here, let's say we have some performance parameter. We're going to call it U1. So something we want to measure the performance of. If we assume U1 depends on some other parameters, say U2, U3, so on, up to UN, Buckingham pi theorem is able to distill this problem into something that looks like this. So pi1 is some function g of pi2, pi3, so on, up to pi k. Again, the notation has changed. So n is the number of variables, I'll say dimensional variables. So the number of dimensions in these variables is j. This number k is the number of dimensionless groups. K equals, I guess, n minus j in the ideal case. So this is a powerful theorem because if you were, say, to run an experiment and you're trying to characterize this relationship, so you don't know what F is, but you know, say this U1, let me give an example, is the lift force on a wing, and you know that it depends on things like the speed, the density, viscosity, so on. So the cost of this first set of experiments, if you had to characterize, say you're just trying to design an experiment and you want to test 10 different values of each of these parameters to determine a function U1. So the cost of that first experiment, let's say each experimental run costs you $sign. The cost of that first one is $signs to the n. The cost of this experiment here is $signs to the k, where k is less than n. So we're going to do a lift coefficient example later on of Buckingham pi theorem. But say the lift coefficient depends on 6 or 7 dimensional the lift force depends on 6 or 7 dimensional variables. We'll see that the lift coefficient only depends on, say, 3 dimensionless variables. So you only have to if you want to compute the, if you want to estimate the performance of something in terms of lift, you only have to measure the non-dimensional variables. So the cost will go down, basically. This is an advantage I gave of doing these dimensionless tests, is the reduced cost, okay? So there's kind of a, how Buckingham pi theorem usually works is there's kind of an algorithm you work through for every problem. So I'm just going to basically give you the steps as I'm working through a problem. I think that's the simplest way. Let's do an example. So I usually word this as generate a non-dimensional relationship for lift over an airfoil. Okay. So the first step in Buckingham pi theorem is to list. Gee, I'm going to color code the steps as red just so they stand out a little bit. List the dimensional variables involved. So the variables, the lift force is some function of, and now we kind of have to brainstorm of what the lift force on an airfoil might depend on. So maybe you guys can help me. Any variable. Yep. The speed, right. So like with a given airfoil, if we have a higher speed, we'll get more lift, right? Yep. Viscosity, okay. So we're going to use mu here. Okay. Anything else? Yeah, maybe you please. The shape of the airfoil. That's a good one. So the shape, um, we assume geometric similarity. So we're going to basically have we're going to test a scale model of this shape. The lift will depend on sort of the size of the airfoil, right? Like if we have a really big wing, we'll get more lift. So that's not exactly the same as shape, but shape would basically be like accounted for in geometric similarity. So size we'll kind of notate by C. So C is the chord length. The other variables, yep. Angle of attack, right? So angle of attack is like if you have a wing that's flying like this, and then you steepen the angle of attack, you'll generate more lift. You'll also generate more drag, but you generate more lift that way. Any other variables? Yep. The turbulence of the air. So that's a good one. The turbulence of the air will kind of be a function of the Reynolds number, if that makes sense. So we're going to derive the Reynolds number as part of this. So basically, in order to characterize the effect of turbulence on lift force, we'll study it at different Reynolds numbers, because if that makes sense. Yeah, maybe we'll come back to that later. Yes? The area of the wing. Okay, that's a good one. So if the area is bigger, then we're going to get a bigger lift force. For now, I'm going to assume, let's assume that we're going to do an airfoil, so a 2D shape. So an airfoil is just kind of an infinitely long, we're not going to take a three-dimensional effect in, but after this, I will talk about three-dimensional effects. Yep. Great, the density of the fluid. So if you take the same airfoil and put it in, say, air versus water at the same speed, you'll get a different lift. In that case, the viscosity will also have changed, but the density change is much bigger. Okay, well, that's pretty much I have for the first part of this example. Okay, so we have our performance parameter as in a function of these variables. So in this case, So in this case, we have n equals, someone have a guess of what n is here? So n is the number of dimensional variables. How many dimensional variables are in this relationship? 5? Okay, good. Yeah, so why do you say 5? Yep. Sorry, did you say 5? Oh, yeah. Oh, okay. Yeah, so Aaron, do you have a different answer than 5? Oh, okay. Does anyone have a guess why it's 5? Yep. The function is based on 5 parameters. Okay. Yep. Do you have a different answer? Yeah, these are all very good questions. This is kind of confusing. Okay, so technically, don't think too much about the dimensions at this stage. So n in this case is going to be 6. So we have 1, 2, 3, 4, 5, 6. So angle of attack, you're right. It's a dimensionless variable, but we're going to see that basically just means it's one of our pi groups automatically. We don't have to do analysis with it. So it's kind of a trick question. Sorry for asking that. So we have, say, n equals 6 dimensional variables. We're going to pretend, oh, we don't know what the dimensions of angle of attack are. Okay. So you start with the number of basically dimensional variables at this stage, n equals 6. The second step is to list maybe, dimensional variables isn't the best name for this stage because, like, for example, angle of attack doesn't have dimensions. It's kind of the number of like original variables or intuitive variables involved. Okay. Second step is to list the dimensions of each variable. So now we've got to go through and list the dimensions of all these variables we have. So we have mass. So I'm going to denote m as mass, say SI units of kilograms, but actually the actual unit system we're going to use doesn't matter. L has length, is in meters. T is time, and that's in seconds. So our variables are FL, the lift force, that has dimensions MLT to the negative 2. So kilogram meter per second squared. You can think of that as like MA, so kilogram times meter per second squared. L is a length. So what will the dimensions of some length be? Okay, I'll do this one, but you guys are going to have to help me later. L is just L. Okay, that L is not the same L. It's like the L is the length variable, but it just has dimensions of length. Okay, so rho, what would the dimensions of rho be? I hear people are slowly getting there. Anyone want to take a guess? Yep. Yep. Mass L to the negative 3. Okay. Mu. Okay, so mu has units of pascals times seconds. Pascal is a Newton per meter squared times seconds. And a Newton is kilogram meter per second squared over meter squared times seconds. So long story short, mu is m L to the negative 1, T to the negative 1. Yeah, okay. U. Anyone have a guess for U? Yep. L T to the negative 1, right? Okay, what else did we see? Okay, so actually this L is different in my notes, but we basically called that C, chord length, some sort of length scale. So that's, sorry about that. This C is this C. Okay, we've done all of our variables except angle of attack. So angle of attack has units of degrees or radians. It actually turns out that that's unitless. So angles technically aren't a unit. It's kind of a amount of a full circle that you can think of it like a degree being like an amount of a full circle. It's more of like a, I guess, a ratio or percentage. It's an amount. So the angle of attack is unitless. So for this stage of Buckingham pi theorem problems, there's a really useful table that I gave in the. So this table here basically gives you that MLT representation for whatever variable you would want to use. So this is a table out of the White Fluid Mechanics book. I believe this is table 5.1. So all these different things. For example, like force, we said that was, sorry, force is here. So MLT to the -2. So kilogram meters per second squared. Okay, so that's a useful table if you want to say check, or if you don't trust your own, I guess, unit derivation here, especially for things like mu. Okay, so we've listed now the dimensions of each variable. Step 3 is find j. Okay, so j is the number of dimensions in our problem. So how many different dimensions do we have here? Of primary dimensions. 3? Is that what you're saying? Okay, let's do a show of hands. Who thinks it's 3? Okay, it's 3. So j is 3 because we have mass, length, and time. All of the dimensions, all of our sub variables are made up of 3 different dimensions. They're just different combinations of mass, length, and time. If we had temperature, that would be an additional one, because temperature, say in Kelvin, you can't represent a Kelvin in like kilogram meters per second. Like it's a fundamental unit, basically, is temperature. So in that white table, the big theta there is temperature. So they couldn't use T because T was already taken by time. And so I'm not sure why they picked theta for temperature, but theta is the units of temperature. So here you see like temperature. So temperature as a variable just has units of theta. So it's a degree, or it's like a Kelvin or Celsius. The whole point of this is that it doesn't actually matter the unit system we're using. Okay, so we said J equals number of primary dimensions equals 3. So MLT. This means now we can find K. So K is N minus J. You go back up to the theorem at the top. So N is the number of variables in our dimensional relationship. J is the number of primary dimensions. And then K is the number of dimensionless groups that we expect to form. Okay, so we said N was 6. J was 3, so K is going to be 3. Does anyone have questions about why K is 3 here? Why N is 6? Why J is? No? Okay. I know 6 minus 3 isn't the hard part of this problem. Okay, so we found K. So we expect to form 3 dimensionless groups. That's what that means. Step 4 is select J scaling parameters that do not form a dimensionless group. These are called repeating variables. So our J is 3. We have 3 primary dimensions. So we need to pick 3 of these variables to form our repeating variables. So this is probably the most, I guess, hardest part when you're learning how to do these problems is going to be picking these J scaling parameters, because it's very important for your basically your own sanity that you pick them well. But there's really no guidelines as to what you pick for them, other than pick simple variables, okay? And pick the numbers that you pick, they can't form their own dimensionless group, and they have to have all of the dimensions in our problem. So I'll give some guidelines later on. So I'll summarize what I just said later on. But our simple variables, maybe, what do you guys think is the simplest variable here? With not alpha. So what do you think is the simplest variable? C, chord length. Okay. So let's pick C. Okay. Now I'm going to pick U because I think that's a relatively simple variable, LT to the -1. It's maybe not the most simple variable here, but we're going to pick rho. This is a very good recommendation in general. So pick C, U, and rho, or pick L, U, and rho, a length scale, velocity, and a density for these repeating variables. Okay. This will come a little bit with experience, but this is a good general recommendation as a starting point. Pick simple variables and pick C, U, and rho. Are there any questions on that? As you do more examples, you'll kind of get a feeling for which variables you're supposed to be picking for these. If you go through the analysis and you pick repeating variables and you find yourself getting stuck or overly complicated, or you don't recognize the dimensionless numbers you're getting out, that means you probably picked the wrong repeating variables. So that's a good gut check. Is this analysis almost always produces numbers that you've seen before, dimensionless numbers that you've seen before. Okay, so step 5 is, okay, I'll say form pi groups. By adding one remaining variable at a time to the repeating variables. Determine exponents that make the product dimensionless. So what do I mean by that? So we picked these repeating variables here. Okay, so we picked these repeating variables, C, U, and rho here. So our remaining variables, our FL, mu, and alpha, right? Because we picked C, rho, and mu, and U. So each of our pi groups is formed by by multiplying our repeating parameters by one of these. So we're going to get 3 pi groups, right? K is 3. One pi group will come from FL times our repeating parameters. One pi group will come from mu times our repeating parameters. One pi group is going to come from alpha times our repeating parameters, which ends up just being alpha. We'll see that. So the first variable, the first pi group we're going to do, we'll call it pi1. We're going to multiply FL by L, some exponent, U to some exponent, and rho to some exponent. So these are our repeating parameters. Pi1 is the first pi group. So we know that this needs to be dimensionless. So what we basically get here is a system of equations that we can use to determine A, B, and C. So we have 3 dimensions in this problem, mass, length, and time. And we have 3 unknowns right now, the exponents A, B, and C. So we need to build our system of equations. So let's look at the N system of equations. So force has units kilogram meter per second squared. So that's m to the 1. Again, you can go and look up this table. So m to the 1 plus, sorry, I called this L again. This is C. It's just the length scale that we're using in our problem. So that there's no kilograms in our length scale. It just says units of meters, right? Same with velocity. There's no kilograms. It's just meters per second. There is a length scale in our density. So that means density is kilograms per meters cubed. So that's just C equals 0. So this equals 0 is because dimensionless. Does anyone have questions of where this has come from? Yep.
So that C is a different C than the chord length.
Yeah, it is. And the L is a different L than whatever I said earlier. So that C is just the exponent of the rho. Yeah, sorry about that. This C is not the same as this C, just to clarify, but good question. Any other question? Yep. Sorry, I'll get you after. Yeah. No. Yep. Good. Yep.
It's not pi.
Right. Yeah. Pi is a variable. Yep.
Where did the 1 come from?
The 1 comes from, we said we're going to do force to the 1. So there's no unknown there. We're just going to multiply force, which is one of our remaining variables, by our repeating variables each raised to some power. That's the core of this step in the process. So that's where the 1 comes from. Any other questions? Okay, so this actually tells us directly now we can solve this equation of C equals -1, right? So whatever our pi group is, it's going to have C on the denominator. Let's look at our length dimension. So what is the first? What is F? FL has units of length to the 1. So again, that's 1. And that's because FL is kilogram meter per second squared. So kilogram to the 1, meter to the 1. That's where that 1 comes from. I guess what comes next? Maybe someone can help me. Yep.
So A, which is for C, is also 1.
Right? Okay. Anything else? Any?
B.
Sorry?
At B.
At B, right? Anything else? So we said density was kilograms per meter cubed, right? So it's actually going to be minus 3C. What does that equal? 0. Good. Because it's dimensionless. Let's just summarize where these came from. The 1 came from the exponent on FL and the fact that FL is kilogram meter per second squared. so the meter to the 1. The a comes from the exponent on c, the chord length, which has units of meter, just to the 1. The b comes from the exponent on u, which has units of meters to the 1 second per second. So that's why this is 1. And density is units of kilograms per meter cubed. So the meter is on the denominator and it's to the 3rd power. So that's why it's minus 3c. We already solved for c, so we will replace that eventually if you're wondering. But let's do our last equation here. Okay, so what's the first entry in this equation? -2, right? Because our force has units nLt to the -2. So kilograms meters per second squared. So -2 plus, okay, I'll just go. So minus b, minus, okay, minus b, because b is meters per second. Again, equals 0. All of these equations are equal to 0. So usually you set up the equations before solving, like for C, like what I did here, but just in the interest of time, I'm going to give us the solution of what we would get solving this solution of a system of equations. We get A equals -2, B equals -2, C equals -1. I know I skipped the solution there, but I think that's okay. Are there any questions about the setup of the system of equations? Okay. So this means that pi1 is FL over C, I'll say rho u squared c squared. Okay. Does someone recognize this non-dimensional group? Or is it close to some that you've already seen? Yep. Yeah, it's pretty close to lift coefficient, right? So if we go to this handy table in the white book, I went through some of these non-dimensional parameters last time, but here's a massive table of non-dimensional parameters. Let's look at lift coefficient here. It's L over 1/2 rho u squared a, where a is an area scale. So we actually have something that's quite close to that. We're missing the 1/2, but Buckingham pi won't tell us about this 1/2 here. So we basically derive the lift coefficient now. So without, if you guys aren't familiar, this term means without loss of generality, we can say pi1 is CL, which is FL, or 1/2 rho u squared a. The reason we can just drop in a for c is it doesn't actually matter the definition of this variable. It's just some scale that we think depends on. Okay, so we basically discovered the lift coefficient here. It's the ratio of force to some rho u squared times a length scale squared. Let's do pi2 now. Pi2. What is our next remaining variable? Remember, what we're doing right now is finding our 3 pi groups. So we did FL. What is our next remaining variable that we haven't selected as a repeating variable? Mu? Yeah, good. So it's mu. So these are repeating variables. So our next remaining variable is mu. So it's the same, it's going to look exactly the same. So mu times c to the a, what did I say? U, and then c to the a, u to the b, rho to the c. Again, apologies, these c's are not the same thing. So we're going to do the same system of equations, just using mu now. So you'll notice in this system of equations, kind of this part doesn't really change. What changes is this constant part coming from our remaining variable. So that's a tip to save yourself time. If you have a lot of pi groups on an exam, the only thing that's going to change equation to equation is the constant part, because you know that's the dimensional part of this is always going to be the same combination of unknowns. So with mu, we'll get this system of unknowns. MLT. So mu has units of mass to the 1. So it's going to be 1, again, plus c equals 0. Mu has units of length to the negative 1. So that would be minus 1 plus a plus b minus 3c equals 0. So again, this part didn't change, right? The plus c is the same. Now, since mu has units of length to the negative 1, this negative 1 changed. The time system of equations, so mu has units of time to the negative 1. Negative 1 minus b. This yields a equals b equals c equals negative 1. Okay, so let's see what this variable is. Pi 2 equals mu over rho u c. So I sped through the system of equations there. Let me just take a step back. Does anyone have questions about how this system of equations was derived? Not about that. You guys are okay with that? Okay, so let's move on to the solution of this system of equations. It gives us mu over rho uc. So what does this number look like? Yep.
It looks like 1 over the Reynolds number.
Yeah, it looks like 1 over the Reynolds number, right? So this is actually 1 over the Reynolds number. So what you do is when you get your non-dimensional thing, you come to this table. If you don't immediately recognize that it's 1 over the Reynolds number, and you kind of look, you're looking for things that have rho, u, a length scale, and mu. Oh, that looks like the first thing in the table, which is Reynolds number. Now, again, without loss of generality, we can say pi 2 is the Reynolds number. Since the Reynolds number is non-dimensional, 1 over the Reynolds number is still non-dimensional. We didn't change the units. You can't change the units of something that's non-dimensional by just dividing it, going 1 over it. Okay, now pi 3, our last non-repeating variable is alpha, which is unitless. So I'll show this the first time, but you don't need to show this every time. Basically, since alpha is unitless, this is just going to yield a equals b equals c equals 0. Therefore, pi 3 is just alpha. So we have our 3 pi's. The last step, what's step number 1? 6? Okay. Last step is state the non-dimensional relationship. So our original relationship was FL is some function C rho u mu alpha. So we had 6 variables. And we found this. We found FL over rho u squared c squared is some function g, probably a different function, of mu over rho ul, sorry, c and alpha. So these are our pi 1, pi 2, pi 3. So basically we discovered that the lift coefficient depends on Reynolds number and angle of attack. So g is just some function, just like f is some function. So we took this basically from 5 variables and distilled it down to 2 variables. And for incompressible flows over a 2D airfoil, this is true. So the only thing that will change your lift coefficient is if your Reynolds number changes or if your angle of attack changes. It doesn't matter if your viscosity and all that stuff changes. As long as those are held constant, you'll get the same lift coefficient. Are there any questions about how I put this together? Yep.
Back to the start. At the beginning, we list dimensional variables involved. So what happens if you didn't consider all the variables involved?
Then you might not get the right answer. The good news is I know that listing those variables is quite hard. So I will basically, like, if I ask you to do that, I'll say, oh, you think kind of your intuition tells you it depends on the following variables. That makes sense. Because, yeah, I know you don't know all the different variables that lift coefficient depends on. So it's kind of unfair to. Okay, yes?
When you're choosing your repeating parameters,
Yep.
how many how many solutions can there be by choosing different setters? Or usually just like the way you did it is the
A number of solutions is sorry, the number of solutions to the system, say, of equations, or
no. I mean like so
number.
Pick a different group of root parameters.
Yeah. Yeah.
Yeah. Are there multiple answers usually, or is it common in just one?
Yeah. There's no unique answer, but it will basically get very ugly. So the recommendation I have is pick these, but remember if there's additional variables, say I say it depended on temperature, you need to add an additional variable that depends on temperature into these repeating variables. Okay, Aaron? It's a good question, and I thought you guys were probably going to ask that. So the question is, will I give you this on the test? So let's have an agreement. I will give you the one on the right-hand side because this is a hideously long table, and that's going to take up like half your formula sheet. This one here, I don't think I will give you that. I think that these are, if you put the common ones on there, that's fine. But I will give you the list of all these relevant non-dimensional parameters. I think that's fair. Any other questions? Okay. So there's only 2 minutes left in this lecture. So I have some basically guidance and tips for each of these steps. So I'm going to read them basically verbally, and I'll include them on the notes that I post online. But for now, I guess you can just listen. So for listing the relevant dimensional variables, I told you I will basically give you those. But if you had to do this in real life, say you're analyzing a new fluid phenomena, usually what you do is you kind of look at that table, that left table, and you say, what variables do I think actually are involved in this problem? And then you add those into your list. Okay? Remember that you have to list the quantity of interest. So the quantity of interest here was the lift force. So we had to list that as one of our variables. Right? So lift force has to be listed as one of the variables. So for selecting repeating parameters, I mentioned this when I was doing it. You need to choose J repeating parameters, the number of dimensions, repeating parameters. The repeating parameters can't form their own dimensionless group. So in this case, the repeating parameters we picked, they can't form their own dimensionless groups because this has meters per second, and this is kilograms per meters cubed. So no matter what way you combine that, there's no way you can get a dimensionless group because they all have different units involved in them. Don't pick the quantity of interest as a repeating parameter. So I didn't pick lift force as repeating parameter here because we want to basically isolate that as one of our pi groups. So don't pick the parameter of interest. Again, you have to contain all the primary dimensions in the problem. So I picked these, mass, length, and time is repeated here. If I picked, say, be a terrible choice, but say I picked U, C, and alpha, I don't actually have mass anywhere in my repeating parameters list. So how can I form a dimensionless group? You can't, because you can't cancel the mass with anything. Okay, so you need to have all the quantities of interest in that group. So forming the pi groups, once you do basically one or two more of these, you're going to see that they all start churning out very similar numbers to the ones that are in this table. So start kind of with the end in mind of the pi group you're looking at. So if you say, like, I'm going to have a force times these repeating parameters, I'm probably going to end up with some sort of force coefficient. Or mu times that repeating parameters, I'm probably going to end up with Reynolds number. So keep that in mind. Don't feel like you have to do this from scratch every time. And yeah, so look at those common non-dimensional groups.